Hello everyone. I'm taking this step in putting forward a small video series on the physics calorimetry chapter for ICSE class 10. I'll be dividing this video series in three parts. Each will be max of 10 minutes. So as we can see, this is the first part out of those three parts. In this chapter, we will be taking majorly numericals because this is one such chapter in physics where numericals carry more weightage as compared to theory. And having seen the difficulty level of this chapter, I have divided this chapter in three uh, types of problem, and that describes the various three parts. Here we can see a small tabular format of all the physical parameters, their symbol and their SI unit. In physics, what I believe that until and unless you are thorough with the units, your concept will still be unclear. So these are the only 7 parameters we will be using every now and then, and in K denotion, how we denote them and what are the SI units are very important. Heat, throughout this chapter we'll be using heat with capital Q, and it will be measured in joule. One other unit of heat is calorie, but we'll be having very less number of questions with calorie. Majorly we'll be using joule. Temperature, as we all know, it is denoted by capital T and the SI unit is Kelvin, capital K. Change in temperature, it is an important parameter. It is denoted by delta T. We shall keep in mind that change in temperature is same as we measure in Kelvin or in degrees Celsius. So for change in temperature, suppose they have given you the change in temperature is 5 degrees Celsius. That is also equal to 5 Kelvin. Suppose initial temperature is 30 degrees Celsius and final temperature is 50 degrees Celsius. The change in temperature is 50 minus 30 will give you 20 degrees Celsius. It is the same in Kelvin scale as well. It will be 20 Kelvin. So we will see the application of this thing in many problems. Heat capacity, specific heat capacity. These are two terms, look similar. याद रखेंगे, heat capacity is denoted by capital C, and specific heat capacity, 90% time we are going to use the small c only. If it's only heat capacity, we won't be having the mass term. We don't have kg or gram here. But in case of heat capacity, specific heat capacity, we are having a term called kg. And as both will have a hairline difference of a formula also. So it is just joule per Kelvin or joule per degree Celsius. As I just said, Kelvin and degree Celsius in delta T parameter is same. So it is joule per Kelvin or joule per degree Celsius. And here it is joule per Kelvin per kg or joule per degree Celsius per kg. So इस बात को याद रखना है, heat capacity capital C, specific heat capacity will be small c, or vice versa we can say. If the mass unit is given, it will be specific heat capacity. If the mass unit is not given, it will definitely be just heat capacity. And majority problems will be dealing with specific heat capacity. Now we have another term called specific latent heat. It is denoted by capital L, and we have just joule per kg here. This is very important parameter for the third part of this video series, because specific latent heat is generally used only during change of phase. Water is getting converted into ice or water is getting converted into steam. यहाँ पे change of phase, change of state of matter is involved. So water to ice will be liquid to solid. In that case, the parameter which we consider is specific latent heat. So we'll deal with this in the third part of the video. And last but not the least, power. It is of course denoted in with P, and it's measured in watt. We have one more higher unit of power, which is called horsepower, denoted with HP, and we know that 1 horsepower is equal to 746 watt. It's a very famous and very favorite question of ICSE. Moving forward, we can see I'm putting forward a list of formulae. The first formula being Q is equal to mc del T. Q हमने denote किया था heat energy के लिए. Of course, we are going to measure in joule. M is mass of the substance. It is small c, so specific heat capacity. It is delta T, change in temperature. So again, here we can see mass is measured in kg, specific heat capacity joule per kg per Kelvin, and change in temperature, it is either Kelvin or degree Celsius. Just because it is changed, it can be same. It is same in both the unit. So this is one formula. Q is equal to mc del T. You have to memorize the formula. We don't have much formula. I think six or seven in numbers. Second one being capital C is equal to mc. What is capital C? Heat capacity. M is mass. Small c, specific heat capacity. So this is the relation between capital C and mc, that if you want to find just heat capacity, you got to multiply specific heat capacity with the mass. Or look at this formula. Q is equal to mc del T. Just now we said mc means capital C. So instead of this mc, if we write capital C, so let me do it for you. So instead of this mc, if we write capital C and after that we have a del T, so we can say C is equal to Q upon del T. So this capital C is equal to Q upon del T. That is yet another formula here. C is equal to Q upon del T. So moving forward, now we're coming to Q is equal to ML. This formula we are going to use in the third video, as I discussed already, because it is involving latent heat, specific latent heat, which is used only when we are going to change the phase of the substance. So we have seen two formula for Q. One is mc del T. This is going to be used when we have a change in temperature involved, not change in phase. And Q equal to ml will be used when we have a change of phase involved, not change of temperature. See, we don't have any temperature change term. So definitely in Q equal to ml format, we won't be having any temperature change. And this is capital C is equal to mass of the substance into specific heat, which is also equal to heat divided by change in temperature. So these are the three simple basic formulas. I request all of you to make a note of this. Just don't simply watch it, uh, see it and copy it down. Fourth formula, again, it is in respect to heat energy. Heat energy is equal to power in time. We have seen in work energy power chapter also that formula for energy is equal to power into time. Power we are going to measure in what? Time. Of course, the SI unit is second. So heat energy is equal to power into time. This is yet another formula which is going to be used very much in this chapter. Coming to fifth one, we can get it from here only. What is the value of small c? Small c will be capital C upon small m. See, look at this part. Just look at this part of the formula. Small c will be capital C upon m. That is what has been written here. Small c is equal to capital C upon m, where capital C denotes the heat capacity, m denotes the mass of the substance. So basically we have seen four formula. This formula is just another derivation of the second formula. Moving forward, formula for principle of calorimeter. This is very important topic of the chapter. We have varieties of numericals from this chapter. What is principle of calorimeter says that heat lost by the hot body is equal to heat gained by the cold body. It is so obvious that when you are going to keep a physical contact between two bodies, one which is at a higher temperature and another one which is at a lower temperature, heat is going to flow from the hot body to the body which is having at a lower temperature, that is to the cold body. When you're placing contact two bodies together, one at a higher temperature, another at a lower temperature, heat will flow from hot body to the cold body. So that is the principle of calorimeter, that heat lost by hot body is equal to heat gained by the cold body. We have two cases here. Case number one, when we don't consider the vessel or the calorimeter which is being used. So in case 1, we have mentioned here calorimeter is not used. Then what happens? This is the equation. M1C1 T1 minus T is equal to M2C2 T minus T2. On the left hand side, the parameters are only for the hot body. On the right hand side, the parameters are for the cold body. So it implies M1C1. Okay, and in the second case, what we have is calorimeter is considered. So in the first case, what we have seen, we have not considered the vessel or the calorimeter which was used. In the second case, we are using the calorimeter. So what is the difference between the first and the second equation? We just have an additional term on the right hand side. This being the additional term. So this being the additional term when the calorimeter is considered. What does it stands for? It stands for, we'll see the denotation now. So what you can see here, M1, mass of the first substance. Of course, we're talking about the first substance as in the hot body. So M1, C1, T1. So all these three parameters, M1, C1, T1, mass of the first substance, specific heat of the first substance, temperature of the first substance. That is so obvious. So as I said, on the left hand side, we have the parameters for the hot body. What is the small t? The small t denotes the final temperature of the mixture. That is so obvious when you are mixing two liquids, one at a higher temperature, one at a lower temperature, they are going to attain an intermediate temperature. We're talking about this T. This small t is the final or intermediate temperature which is being attained after mixing the hot as well as the cold body. So M1C1T1 denotes the mass, specific heat capacity and temperature, initial temperature of the hot body. M2C2T2 denotes the mass of the second substance, specific heat capacity and temperature, that is the lower temperature. These are the two parameters. Initial temperature of the second substance. T2 को हम initial temperature of the second substance भी बोल सकते हैं. Small t we have seen, this is the final temperature of the mixture. Now comes this parameter capital M, capital C, and T minus T2 we have just now seen. So capital M and capital small c, these are two more parameters. Capital M is the mass of the calorimetric substance, because in this case where calorimeter is considered, we have this term. So definitely capital M denotes the mass of the calorimetric substance, like the calorimeter, just material of construction of the substance of the calorimeter. And small c, it is the, of course, specific heat capacity of the substance used in the calorimeter. So these are the two terms. So basic focus you should give on these two formulae. We have, that is the last formula of this chapter. Heat lost by the hot body is equal to heat gained by the cold body. It is called principle of calorimeter. It has also been given a second term called principle of mixtures. That way also they ask the question. Calorimeter is not considered. We have just one term equal to second term. You have to take care of this part. M1 C1 T1 minus T equal to M2 C2 T minus T2. So I'll just tell you one more example here. Suppose I'm denoting hot body with capital H, cold body with capital C. Let us say hot body temperature is 50 degrees Celsius, cold body temperature is 20 degrees Celsius. And let me assume that the intermediate temperature we are going to reach is let us say 30 degrees Celsius. So we can see T1 minus T, it's gonna be 50 minus 30, going to give you a positive value. And here it is T minus T2, that is 30 minus 20, again a positive value. So in that aspect you can memorize the equation that every single time we are going to get a positive value. It is from the left to right, T1 minus T, and on the right hand side it is T minus T2, that's it. And the same T minus T2 is going to come with the calorimetric term also. So it is very easy equation. Both the equations are very easy. We'll see how the numericals are linked with this formula. Moving forward, so we have the questions coming now. It is question 1. We are going to, as I discussed, we are going to see three types. Type 1, we are discussing principle of calorimeter, and here we can see it is what type, case 1 or case 2. Easily it is judgeable that it is case 1, because we have just left hand side equal to right hand side. We don't have that plus mct minus t2 here, so it belongs to the first category where the calorimetric substance is not considered. Let us see what is the question. The question comes as such: a mass of 50 gram of a certain metal at 150 degrees Celsius is immersed in 100 gram of water at 11 degrees Celsius. So after reading the first line itself, you should be in a position to copy down the data. So what is the data? The data talks like this. we have one substance. Acha, you need to understand ki which substance is at higher temperature, the 50 gram metal or the 100 gram water. The temperature of 50 gram metal is 150 degrees Celsius. That is why metal parameters we will take in the first part. So M1 is 50 gram, T1 150 degrees Celsius. We can see specific heat capacity of the metal is not given to us. So there's a question mark here. And on the right hand side, I have taken the cold body parameters. A cold body as in the body at lower temperature. So 100 gram of water. So M2 is 100 gram. The temperature given was 11 degrees Celsius. T2 is 11 degrees Celsius. And at the end, what they have said that assume that the specific heat capacity of water is 4.2. So we have given C2. Why C2? Because water belongs to the second category in the colder half. So C2 is 4.2 joule per gram per Kelvin. See what we have done here, हमने जूल पर ग्राम पर केल्विन को ऑटोमेटिकली जूल पर ग्राम पर डिग्री सेल्सियस कर दिया, because as I said it is all the same. It takes care of the change in temperature, and change in temperature में Kelvin and degree Celsius is same. Why we have done? Because the temperature given to us is in degree Celsius. We don't want to convert them in Kelvin. We want to thoroughly maintain the entire question easily. So C2 को ही हमने instead of Kelvin we have written degree Celsius. The value does not change at all. And they have given the final temperature is 20 degrees Celsius here. So small t is equal to 20 degrees Celsius. So we can see the it is working in synergy. 150 उससे कम 20 उससे कम 11. From left to right the temperature is decreasing. So we are going to maintain that healthy relation. Now calculate the specific heat capacity of the metal. That is so obvious, this parameter was missing. They're asking us to calculate this. So which equation you're going to use? Of course this equation you're going to use. So here comes the equation, M1 C1 T1 minus T equal to M2 C2 T minus T2. Having written the data, then the equation, it is mere substitution. There we go. We have substituted 50. We don't know C1, so C1 as such. T1 minus T is 150 minus 20 in bracket. On the right hand side, you have 100, 4.2, 11. So 100, 4.2, but we are not going to substitute 11 just like that. It is 20 minus 11 as per the formula. So we have 20 minus 11. Now, so 150 minus 20 is 130. 20 minus 11 is 9. And then what will be C1? The right hand side divided by 50 into 130. That is what we have done. And it's mere calculation. You have got this. What is going to be the unit? It is going to be the same unit which C2 was given. C2 was given as joule per gram per Kelvin. We have given joule per gram per Kelvin. Or instead of that also we can write this also, joule per gram per degree Celsius. So I don't think it's too tough a problem. It looks complicated, but once the values are written properly, it is all set. We'll take another question on this. Let us see. Again we can see the question number has changed, but the type is the same. Let us see what is the problem. We have 600 gram of cold water and the temperature rises by 15 degrees Celsius. That means they have not given us the initial temperature of the cold water. They tried to make the question a little complicated, but we'll see how we deal with this. And other substances, 300 gram of hot water. So here both the substances are water only. One is cold water, one is hot water. And the temperature of the hot water, initial temperature was given 50 degrees Celsius. What is the initial temperature of the cold water? Very nice. We can very well judge when they have not given the initial temperature of the cold water. That could be the question, and that is actually the question. Let us see how the parameter goes. What we are going to take in the first part, that is the left hand side. As I discussed, we are going to take the parameters of the hot liquid, and you can see 300 gram of hot water. So 300 is going to become the mass 1. C1 and C2 in this case are going to be same. Why? Because water in both the cases, be it hot water or be it cold water, their specific heat capacity is going to be the same. So the previous question they has given us the data, 4.2 joule per gram per degree Celsius. So both C1 and C2 are same here. Initial temperature of the hot body 50. What I have considered is initial temperature of the cold body, which we need to find. We have taken it at X. And since it is given that the temperature of the cold water rises by 15 degrees Celsius, it is so obvious that the intermediate temperature is going to be X plus 15. So previously the cold body temperature was X, and if it rises by 15 degrees Celsius, it is gonna be X plus 15. So again, like the previous question, we have noted down all the parameters. Equation to be used is m1c1 t1 minus t is equal to m2c2 t minus t2. Mere substitution. Instead of m1c1, 304.2 comes here. T1 50, no issue. T is x plus 15, and since we have a minus sign here, so we got to give a bracket x plus 15. On the right hand side, m2c2 604.2 substituted. T is x plus 15 and T2 is x. So instead of T2 we have put x. Open the brackets. Once we open it, this 3. Acha, in the next step, 4.2 and 4.2 term we have cancelled. Same term from both the side in multiplication format we have just cancelled. So we have remaining 300, and once you open it, open the bracket here, it is 50 minus x minus 15, and the right hand side it is x plus 15 minus x. A little bit of more solving will give us 35 minus x multiplied by 300 on the left hand side, and this x and x cancels, we are left with 15, so 600 into 15. Now solving this, you will get x is equal to 5 degrees Celsius. That means the cold water initially was at 5 degrees Celsius, and if they would have asked what is the final temperature reached, it would have been 5 plus 50, 20 degrees Celsius. But the question only was what was the initial temperature, so initial temperature was 5 degrees Celsius. So this is yet another question, and very good one, because we did not change the method in which we are trying to solve, only they have changed the question. So but our method was intact, and with that method only we have got the answer. Moving forward again, taking the third question comes like this. We have 200 gram of hot water at 80 degrees Celsius, 300 gram of cold water at 10 degrees Celsius. So m1 t1 m2 t2 being given, and since it is water and water, so let us say C1 and C2 is also given, which is equal. Neglecting the heat taken by the container, that is so obvious, we are not taking the heat, we are not considering the heat taken by the container or the vessel or the calorimeter, and that is why we don't have the second term on the right hand side. Calculate the final temperature of the mixture. Final temperature as in they are asking the value of small t. Specific heat capacity of water they have given. So it is very simple. The data comes like this. You need to understand one thing here, very vital thing, that previously how whatever values we have got of specific heat capacity, it was joule per gram per Kelvin. Here what they have given is joule per kg per Kelvin. So since the value is given in kg, it's prime responsibility that you change all this mass values in kg. So in the first thing only we have done 200 gram, that is the hot water parameters, m1 200 gram, then and there we have converted this into kg. So 200 upon 1000 will give you 0.2 kg. That is the first mass we have converted in kg. Here on the right hand side as well, we have 300 gram of cold water, that also we have converted into kg. So 300 upon 1000 will give us 0.3 kg. That was the only conversion we wanted. If we would have proceeded with gram, and here it is specific heated kg, we would have gotten an incorrect answer. C1 4200, C2 4200, same thing. T1 given directly 80 degrees Celsius, and T2 is 10 degrees Celsius. So that also given directly. What we don't have is small t. So let this small t be unknown. Equation, of course, we are going to use this equation. Substituting. So let this t remain as such. So instead of m1, we are not substituting 200. Instead, we are substituting 0.2. So 0.2, 4200, 80 minus t. So obvious because t was unknown. M2, instead of 300 we are putting 0.3 kg, so 0.3 4200 into this t is not known, and T2 value is 10, so t minus 10. We can see 4200 should cancel out, so in the next term we don't have this term, and 0.2 we have converted it into multiplying the entire equation with 10, so we have made it at 2 and this has become 3. So 2 into 80 minus t is equal to 3 into t minus 10. If you open it and solve, you will get this equation followed by this, and finally t value will be 38 degrees Celsius. So hot liquid 80 degrees Celsius mixed with 10 with a liquid at 10 degrees Celsius, the intermediate temperature reached or the final temperature reached is 38 degrees Celsius. So this is the value this value is 38 degrees Celsius, and that was the question. Again, one thing was intact, our method of doing. We did not change the way we are solving the problems. We have seen back to back 3 problems. First problem, they asked us specific heat capacity. Second problem, they asked us, what was the second problem all about? Second problem, they asked us the value of some unknown temperature, initial temperature of the cold liquid. And here we have seen the final temperature, that is the intermediate temperature also. So 3 different questions we have taken, 3 different parameters we have found out, making use of the same way, same method. Moving forward, we have the fourth question, once again on the same formula. So what mass of liquid A? So definitely now the parameter which is missing is mass itself. Of liquid A of specific heat capacity 0.84 at a temperature 40 must be mixed with 100 gram of a liquid B of specific heat capacity 2.1 at 20. So 40 degrees Celsius parameter is missing, mass is missing. 20 degrees Celsius, I think they have given us the mass as well as the specific heat. So the final temperature of the mixture becomes 32. They have given us the value of small t as well. What is missing is M1 is missing. Let us see what are the data we have captured. M1, of course it is not there, so it's a question mark. C1, so hot liquid ka specific heat capacity 0.84 joule per gram per Kelvin, and temperature was 40, so T1 is 40 degrees Celsius. M2 की बात करें, we have 100 degrees Celsius, 2.1, and T2 they have given us 20 degrees Celsius. And what is this 32 degrees Celsius? It is the intermediate temperature. Having noted down the parameters, equation, substitution. Since M1 is unknown, we have made M1 as such. C1 is 0.84, substituted. T1 40, T2 32. So it is 40 minus 32. Moving to the right hand side, M2 C2 is 100 and 2.1, mere substitution. T minus T2 will be 32 minus 20. So 32 minus 20. Calculation, 40 minus 32 will give you 8, and 32 minus 20 will give you 12. Now we got to find M1. So let this right hand side remain as such. Bring these two parameters 0.84 and 8 on the denominator side, on the right hand side. So it becomes like this: 100, 2.112 upon 0.84 into 8. If you calculate it wisely, you will get 375. What is the unit going to be? C1 was gram, C2 was gram, M2 was gram. No unit conversion required. So the answer you have obtained is in grams only. Fourth question back to back on the same formula. All 4 different questions, because they're asking us to find different parameters, but the method we have maintained is same. That accuracy level, that clarity is required in your attempt also. Moving forward, now we're coming to the fifth question. Here what we can see, the formula changed, so it clearly implies that we are considering case 2 of the principle of mixtures. Here we are seeing MCT minus T2, that is capital MCT minus T2 term is getting involved. Means we are not going to ignore, or we are not going to ignore the calorimeter part. Let us see how the question goes. The question talk about a metal piece of mass 20 gram heated to a constant temperature of 100 degrees Celsius. Then it is added in a calorimeter of mass 50 gram. So the calorimeter of mass 50 gram they have mentioned, it clearly implies that we need to consider the calorimeter. So calorimeter of mass 50 gram, specific heat 0.42 joule per gram per Kelvin. This is the small c value for the calorimeter. And the calorimeter contains 50 gram of water at 20 degrees Celsius. So 50 gram is the cold substance mass. 20 degrees Celsius is the T2, that is the initial temperature of the cold substance. And after stirring, the highest temperature is 22 degrees Celsius. That means the small t value, intermediate temperature, is going to be 22 degrees Celsius. Calculate specific heat capacity of metal. Metal we have taken on the first half, that is the left hand side we will take. Let us see, and given the same for water, specific heat capacity of water they have mentioned, C2 value they have mentioned. Let us see how it goes. So these are the parameters given. Mass 1, all higher temperature we are going to see. So mass 1 is 20 gram, T1 is 100 degrees Celsius, C1, specific heat capacity of metal which is missing, it's a question mark. Right hand side will take care of the cold part, that is the lower part, lower temperature part. M2, that liquid was 50 gram, and the liquid which is used is water, so C2 they have mentioned. Given the same for water is 4.2 joule per gram per Kelvin, or I have written in degrees Celsius, it's all the same. And what you need to see, it is given in gram, mass is also in gram, so we don't have to change anything. And the cold water was 20 degrees Celsius, so T2 is 20 degrees Celsius. Intermediate temperature 22 degrees Celsius, we have noted T is equal to 22 degrees Celsius. What's calorimeter is thing? Mass 50 grams, so capital M is 50 gram, small c is 0.42, small c is 0.42. Equation we are going to use is this one. Let us see how it goes. So we can see out of all the 9 parameters, just one is missing. It's a mere substitution and getting the answer. This is the equation. So this calorimetric part I have taken in yet another color that will have the clarity, like why we have added this and how the substitution goes. So M1, C1, T1 minus T, we know M1, that is 20, substituted. C1 we don't know, let it remain as such. T1 minus T is 100 minus 22, 100 minus 22. M2, C2, T minus T2. So M2, C2, 50, 4.2, we have got the values 50 and 4.2. T minus 2 gonna be 22 minus 20, 22 minus 20. This term, capital MC, will get it from here. Capital M 50 gram, capital C 0.42. So 50 into 0.42. And once again, T minus T2, it is 22 minus 20. 22 minus 20. Let us calculate. So this is 20 C1 and 100 minus 22 will give you 78. 50 into 4.2 into this value, 22 minus 20 will give you 2. So you multiply all these values, you will get 420, and multiply all these orange parameters, you will get 42. So on the right hand side, 420 plus 42, what should we have? We should have 462 upon 20, 78. We'll get the value of C1, and C1 is 0.296, and the unit is going to be the same for all the C. So the C here was joule per gram per Kelvin, joule per gram per degree Celsius. So we can write joule per gram per Kelvin or joule per gram per degree Celsius. That is the answer. Again, the method is same, but we have used the second form of the principle of calorimeter. Moving on, let us see the last question of this video. In the for the case of case 2, where we are considering the calorimeter, I've taken one more question on this. That is, this is the question. We have 40 gram of water at 60 degrees Celsius. Okay, it is poured into a vessel containing 50 gram of water at 20 degrees Celsius. That means hot liquid, mass and temperature, cold liquid, mass and temperature. Final temperature of the mixture is 30 degrees Celsius. So final temperature, that is small t value, intermediate temperature भी पता चल गया हमें. Taking the specific heat capacity of water as itna, calculate the heat capacity of the vessel. Right. See, calculate the heat capacity of the vessel. They did not write specific heat capacity. Calculate the heat capacity of the vessel. If you can recall, in this video only what we have discussed, that heat capacity, this term heat capacity is denoted by capital C, which is equal to mass into small c, right? That they want us to calculate the capital C, means this right hand side, instead of mass into small c, we can write capital C, and then in bracket we can write T minus T2. That is what they want, the capital C for the calorimeter, because they have not given us the mass of the calorimeter also, and they have mentioned calculate the heat capacity, not the specific heat capacity. If it would have been specific heat capacity, they would have talked about the small c. They are asking heat capacity, that means they want capital C for the vessel. What is capital for C for the vessel? Mass of the vessel into small c. So this mass of the vessel into small c we have substituted with capital C. We'll see how the formula goes here. So these are the parameters given: mass 1, C1, T1, 44.260 of the hot water, and M2, C2, T2, 50, 20 and 4.2 for the cold water. Let us see what are given for the vessel. Intermediate temperature 30 degrees Celsius. Both capital M and small c are missing. That is, the mass of the vessel is missing. mass of the calorimetric substance is missing, and specific heat capacity of the calorimetric substance is missing. So we'll use the same formula once again. M1 C1 T1 minus T equal to M2 C2 T minus T2 MCT minus T2. In the next step itself, we are substituting. So all these parameters we know: M1 C1 44.2, T1 minus T 60 minus 30, that is 60 minus 30. M2 C2 is 50 and 4.2, so 50 and 4.2. T minus T2 is 30 minus 20, so 30 minus 20. This capital M and small c we don't know, let it be like this. T minus T2 is 30 minus 20, 30 minus 20. So now in the next step, this capital M and C we are substituted with capital C. Just now as I said, substitute this capital M and small c with capital C. That is what we have done. And 30 minus 20 will give us 10. 60 minus 30 will give us 30. 30 minus 20 will give us 10. Now it's a mere calculation now. So the left hand side becomes 5040. Right hand side first term is 2100 and second term is 10 multiplied by C. So C value will be 5040 minus 2100 upon 10, and this will give us 294. Now you got to understand the unit. So हमने जो first वीडियो के एकदम स्टार्टिंग में देखा था, यूनिट ऑफ हीट कैपेसिटी क्या होता है, वी डोंट हैव अ मास टर्म, सो द आंसर इज जूल पर केल्विन. अगर स्पेसिफिक हीट कैपेसिटी होता तो जूल पर ग्राम पर केल्विन होता, but it is heat capacity, we don't have a mass term, we have the answer in joule per kelvin. So I think this will be all in this video. Description of the second part and the third part will be, sorry, link for the second part and the third part will be given in the description. Do watch them, and we have planned a total of 15 numericals, so we could see the 6 numericals were not as tough as they look like. That will be all with this video. Thank you.